Still session 2.3 today. Two topics. In the first topic, I want to show you more examples about direct substitution. Topic 2, we will learn squeeze theorem. Some people call this theorem sandwich theorem. Take a review and preparation. Here are some algebraic formulas that we often use. These formulas are fundamental. Formula A plus B squared is equal to A squared plus 2AB plus B squared. How to see this formula? Write the left-hand side as x plus b times x plus b. Then expand the product by distribution. Then we have this equation. Combine the middle two terms, then we have this equation. This is the right-hand side of the formula. Formula B. A plus B to the third is equal to this. To see this formula, similarly, write the left-hand side as A plus B times A plus B times A plus B. Then expand the two products by distribution. Then we will have this equation. Formula C, A minus B times A plus B is equal to A squared minus B squared. To see this equation, expand the product by distribution. Then some cancellations. Then we have the right-hand side. One remark about formula C. People usually call the factor A minus B the algebraic conjugate of the factor A plus B. Reversely, people also call A plus B the algebraic conjugate of A minus B. So A minus B, A plus B, they are the algebraic conjugate to each other. Review number 2, direct substitution. To compute a limit, we just need to plug in the point A in X. That is, we just need to compute the function value at the point A. Sometimes function at the point A is not defined, or the function value at the point A is not computable. In that case, you need to simplify the function. Then apply direct substitution again. Now, topic 1. More examples about direct substitution. Example 1. Evaluate this limit if the limit exists. When the limit doesn't exist, when the function approaches more than one number, then the limit doesn't exist. Evaluate this limit first by a numerical method, that is, by table. Then by an analytical method, that is, by limit laws, usually direct substitution. Here is the solution to part A. To find the limit, I make this table. The first column is for X, independent variable. The second column is for 1 over X. Third column is for the second term of the function. The last column for the whole function. Now, I let X approach 0 by taking on these numbers. by a calculator, I evaluate the values of the first term, second term, and the whole function on these values. Now, from this table, we can see that as x approaches 0, first term of the function approaches infinity. The second term also approaches infinity. The first term minus the second term approaches some number. I cannot exactly tell the value of that number. I can only tell the first few digits of the number. This number is the limit of the function. So as x approaches 0, the function approaches this number. Part B. Find the limit by limit laws. Here I only use direct substitution. To find this limit, I directly plug in 0 in x to get this equation. But 1 over 0 minus 7 over 0 is not computable. So direct substitution fails. To find the limit, we need to simplify the function f, now this time by common denominator. I factor this denominator into x times x plus 7. Now, to make the two denominators the same, in the first term, I multiply 1 by x plus 7, multiply x by x plus 7. Now, the two denominators are equal, so I can combine these two terms to get this equation. Cancel the number 7, then we have this equation. Cancel x, then we have this equation. Now, to find this limit, direct substitution, plug in 0 in x. So this limit is equal to this number. This number is 1/7. So it turns out that this number is 1 over 7, the exact value. Example 2, evaluate this limit first by a numerical method, then by an analytical method. Here is the solution to part A. To find the limit, I make this table. The first column is independent variable x. Second column is the numerator of the function. Third column, denominator of the function. And the last column is the function. Now, from this table, we can see that as x is getting closer and closer to the number 2, numerator is closer and closer to the number 0. Denominator is approaching 0. But the function, numerator over denominator, is approaching some number. I guess this number is 2/3, but just a guess. Part B. Find the limit by an analytical method, that is, by limit laws. Again, I only use direct substitution. By direct substitution, to find this limit, we just need to plug in the number 2 in x to get this number. This number is 0 over 0. It is not computable. So the first try of the direct substitution fails. To find the limit, we simplify the function, this time by algebraic conjugate, that is, by using this formula. I want to use the square here to cancel the square root. To use this formula, I multiply the numerator by its conjugate, a minus 3 times a plus 3, and also multiply the denominator by the same quantity. This quotient is 1, so I only multiply the function by 1. I haven't changed the function. A fraction times a fraction is equal to the numerator times the numerator, and the denominator times the denominator. So we have this equation. The product on the top, I can use this formula. A minus B times A plus B. So by formula, it is A squared minus B squared. Square root and square can be canceled, so we have this equation. Now simplify the top and factor the number 4 out. Then we have this equation. Cancel x minus 2 from the top and from the bottom. We have this equation. To find this limit, direct substitution again, plug in the number 2 in x, then this limit is equal to this number. This number is 2/3. So the limit in part A, this limit is 2/3. When we use direct substitution to find a limit, we usually need to simplify the function f. Here is a summary about how to simplify the function f in general. There are 4 cases. Case 1, when a function is a polynomial over a polynomial. This is one example. Then to simplify the function, factor the polynomials and then cancel out some factors from the top and from the bottom. Case 2, when a function has a power, this is one example. The function has a power. In this case, expand the power. Then you will see some cancellations. Case number 3, when a function is a fraction minus or plus a fraction. Here is one example, a fraction minus a fraction. Now, in this case, how to simplify the function? Use common denominator. Case number 4, when a function has a square root. This is one example. This case, we simplify the function by algebraic conjugate. That is, we use this formula to simplify the function. Now, topic 2, squeeze theorem. Direct substitution is powerful, but not perfect. In fact, no method is perfect. For example, a numerical method is perfect? No. Usually, a numerical method cannot find the exact value of a limit, can only give us a guess about the limit. The problem with direct substitution is not every function can be simplified. For example, consider this limit By direct substitution, to find this limit, we plug in 0 in x, but then we will find that the function is not defined as 0. Then we need to simplify the function to find the limit. But this function is none of these 4 cases. How to simplify the function? Some people may say that we can cancel 1x from x squared and from 1 over x to get this function. But this is wrong. You cannot ignore the sign between x squared and 1 over x and directly cancel x in this way. So we don't have this equation. When a function cannot be simplified, direct substitution fails to tell the limit. In this case, you should use a numerical method, namely use a table to find the limit, or use the squeeze theorem below to find the limit. The squeeze theorem is easy to understand if you plot a diagram about the theorem. Assume that we have 3 functions, FL, F, and FU. These functions satisfy these 2 inequalities. Because this relation among the functions looks like a sandwich, some people like to call this theorem the sandwich theorem. Here is a diagram about the functions. The blue curve is the graph of the function FL. L means this function is a lower function. The black curve is the graph of the function FU. U means this function is an upper function. And the red curve is the graph of the function F. Because of these inequalities, the red curve lies between the black curve and the blue curve. Now, the theorem says that if as x approaches a, the lower function approaches some number L, and the upper function also approaches the same L. Then the function f is between the lower function and the upper function. Then f also approaches the same L. Here is the case. Suppose point A is here, and this height is the number L. As x approaches the point A, the blue curve approaches this point. This point, the height is L. And the black curve approaches the same point. Because the red curve lies between the black curve and the blue curve. So as x approaches A, the red curve also approaches the same point. This is squeeze theorem. In practice, the lower function and upper functions, FL and FU, are usually more simple than the function f in structure. So this theorem actually is a way to simplify the function f. Here are some examples about how to use the squeeze theorem to find limits. Example 1. Use the squeeze theorem to find this limit. By direct substitution, this limit is equal to this number, but this number is not computable. You can have a try with your calculator. So to find this limit, we need to simplify the function. But this function is not in any of the 4 cases that I mentioned above. So we cannot simplify this function. Therefore, direct substitution fails to find this limit. About this limit, a numerical method works well. Here is a table about the limit. As x approaches 0, the factor x squared. This function has two factors. One is x squared. The other one is sine of 1 over x. As x approaches 0, x squared approaches 0. Sine of 1 over x approaches low number. Sine of 1 over x oscillates between -1 and 1 and approach low number. The function is x squared times sine of 1 over x. The function approaches 0. Therefore, as x approaches 0, the limit is 0. This example requires to use the squeeze theorem to find the limit, not by a table. To use the squeeze theorem, we need to find a lower function and an upper function for the function f. Since sine of anything is always between -1 and +1, so we have these two inequalities. Now I multiply -1 sine of 1 over x and +1 by x squared. X squared is a positive number. Then we have these two inequalities. For example, number -1 is less than or equal to the number +1, less than or equal to the number 7. We can multiply these three numbers by a positive number, say 2, to have these two inequalities. However, if you multiply the three numbers by a negative number, say -2, then we need to change the inequality direction. Because of this sandwich, or because of these two inequalities, a lower function for the function f is negative x squared, and an upper function for the function f is x squared. Now we compute the limit on these two functions. By direct substitution, it's easy to get the limits. As x approaches 0, the lower function approaches 0, and the upper function also approaches 0. So the function f, it is between the lower function and upper function. The function f, the limit as x approaches 0 is 0 by the squeeze theorem. Example 2. Use the squeeze theorem to show that as x approaches 0 from the right side, this function will approach 0. To use the squeeze theorem, we need to find a lower function and an upper function for the function f. Because sine of anything is always between -1 and +1. So we have these two inequalities. Now I multiply -1 sine of pi over x and +1 by this factor. This factor is positive because x is approaching 0 from the right side. From the right side, x is greater than 0. X is positive. So I multiply these three terms by a positive factor. Then we have this sandwich. We have these two inequalities. So this guy is a lower function for the function f, and this is upper function for the function f. Now we compute limits on the lower function and the upper function. By direct substitution, it's easy to see that as x approaches 0 from the right side, the lower function approaches 0. Plug in 0 in x to get the limit. As x approaches 0 from the right side, the upper function also approaches the same number, 0. So therefore, the function f, this is a typo. This function is the function f in the previous example, not this example. So go back to the example. So conclusion is, by using squeeze theorem, as x approaches 0 from the right side, the function f approaches 0 because upper function and lower function, they approach 0. So function f approaches 0 by the squeeze theorem.